Good afternoon, everyone. Thank you for joining our seminar series in financial mathematics and fintech. So today we are very happy to have Dr. Kexin Chen from Hong Kong Polytechnic University to give us a talk about duality in optimal consumption investment problems with alternative data. Before her talk, let me briefly introduce our speaker, Kexin, to all of you. So Kexin is a research assistant professor at Department of Applied Mathematics at the Hong Kong Polytechnic University. So she graduated with her Ph.D. degree in statistics at the Chinese University of Hong Kong under the supervision of Professor Hoi Ying Wong in 2021. Her research interests includes stochastic control and optimization for financial applications, optimal stopping and partial information problem. So her publication have already appeared in many top-tier journals, including the Mathematics of Operations Research, some journal on financial mathematics, and also European Journal of Operational Research, and so on. So without further delay, so let's welcome our speaker, Kexin, to give us the talk. So thank you, Kexin. So you may start.
Yeah, thank you, Patrick, for your very kind introduction. And as you introduced, my today's topic is the duality in optimal consumption investment problems with alternative data. So this is a joint work with Professor Wong. And so let me get started. So consumption investment problem is one most typical and important problem in modern finance theory. And as the natural starting point for the development of a general theory of portfolio choice, Morton initiated the dynamic optimal consumption investment problem study since 1969. So this problem involves the decisions of an investor endowed with some initial wealth and who expect to maximize the expected utility of the consumption over time and also the utility of terminal wealth level. So which is illustrated in this graph. And the utility function U1 and U2 are used to describe the preference of the agent. And these functions are usually increasing and concave due to the risk aversion when exposed to uncertainty. And the relative decisions which are so-called the consumption investment strategies are the consumption rate, and that is the C, and also the monetary investment amount in the risky assets, and that is denoted by pi. And we can see that the wealth level is fluctuated according to the gain and loss of the investment, and meanwhile the investor takes out a certain rate of the amount of his wealth to consume. And Morton's pioneering works promoted researchers to contribute a considerable volume of new work on this subject. And the earlier works focusing on the classical fictionless financial market, which is a geometric running motion that governs the risky asset with constant and known drift term. And this modeling assumption is convenient from the standpoint of analytic tractability, but from a practical point of view, the parameters could be stochastic and unobservable. So to address it, researchers postulate that stochastic factors explain the observed variations in expected asset returns, and furthermore, recent works argue that these factors are not observable. So investors must learn the hidden factors from available information and which lead to the partial information setting. So pioneering work in academic literatures considers dynamic models with the drift driven by unobservable factors. And so these include the linear Gaussian models and also the hidden Markov models. And then apply a filtering technique to estimate them from historical asset price. Well, historical asset prices are a natural choice because they are readily available, relevant, and also timely. It is also worthwhile to explore what additional information can be used and how it can be used to improve the strategy optimality. The technology nowadays enables investors to make decisions using alternative data as a complementary source of observations, and some insights emerge in recent studies include the studies on expert opinion, which is used by practitioners as an additional source of observation that combines subjective views with empirical estimates. And in addition, social media commentary, academic data, and also GPS data are also part of alternative data. And that is the data that originate outside the standard repertory of market data, but are considered to be useful for predicting stock trends. For example, in Pri's work, they show that exploiting Google search trends may lead to profitable stock trading strategies. However, to the best of our knowledge, continuous time investment consumption models have not yet exploited alternative data. So we are interested in the following two questions that are naturally asked. So how to determine the optimal strategy with the advantage of alternative data, and what will be its impact on the decisions? So in our study, we considered the expected return of the risky assets is modulated by a hidden Markov chain, which represent different unobservable economic regimes. And in our model, the investor uses both asset price and alternative data to estimate the hidden state, and then apply these estimates to manage portfolio, investments, and consumption. So we consider the alternative data could be discontinuous, recurrent, and fluctuating, and we therefore incorporate the alternative data into the filtering process that extends the classical one-hot filter to a degenerate jump diffusion with Lavie tap jumps. And these Lavie tap jumps, in fact, it introduced remarkable analytical challenges to the corresponding stochastic control problem, and to resolve the difficulties, we developed a novel duality approach with alternative data, and we linked the dual problem to an optimization problem over a set of equivalent local martingale measures, and devised a methodology to obtain the optimal solution with the alternative data filtering technique. And finally, we demonstrate that the dual problem admits a unique solution for the constant relative risk aversion utility functions. And in addition, we obtain an explicit feedback optimal consumption investment strategy by taking advantage of the alternative data. So now we come to the concrete problem formulation, and we work on a filtered probability space where the F here denotes the full information filtration. And we use alpha to denote the unobservable stochastic factor, so it is a continuous time, finite state, hidden Markov chain. And it represents different economic regimes. And the first component of the observation process is the stock price process, denoted by S. So we model the expected return of it, that is this nu, to be depend on the hidden state. And we model the second component of the observation process, that is the alternative data series. We use eta to denote it as a jump diffusion process. And in addition to the drift part, which is depending on the hidden state, we allow that the Poisson random measure here involved, the intensity measure is given by this form. So which means that the intensity measure could also depend on hidden state. So the inclusion of this measure is essential to address the discontinuous randomness and also the non-Gaussian distribution biases that related to the hidden state. And it also provides well flexibility to model alternative data series from diversified source. So lastly, we use H to denote the available information. So it is the combined filtration that generated by S and also this eta. So here I demonstrate the one example, that is the expert opinions, which is covered by our model. So we consider expert opinions reviewed at discrete time points, such as some own views about the future performance or some economic news. And mathematically, we describe it by the double sequence Tn and Zn, and that is at a random time, Tn, we observe a random variable Zn that follows a distribution density process given by this one, which is dependent on the hidden state. So for example, we can model it as a Gaussian distribution and whose drift is given by this A function depending on alpha Tn, and its volatility given by sigma z. So we can interpret the signal that Gn equals to 0.05 as the view that the stock will grow by 5%. And here the sigma z, it can model the confidence intervals around these expert opinions. And under this setting, if we set eta t as the cumulative expert opinion process, we can finally express it into this integral form. And here the n dt dz, which is a related jump measure, its intensity measure is given by this equation. And to formulate our problem, we first look at the Wells process x pi c, which is corresponding to the choice pi and c, and it involves as this SDE here. And in addition to the regular integrable conditions that placed on pi and c, we additionally require that the Wells level stays non-negative over the whole investment horizon. So we also refer to this constraint as the non-bankruptcy constraint. And in addition, we require that pi and c is age-adapted. So this reflects that only partial information is used in this problem. And the agent aims to maximize the following objective function. So the objective includes the running sum of utility on the consumption, and as well as the utility on the terminal Wells level. So intuitively, the problem is decomposed into two parts. The first is the Bayesian learning or filtering of the hidden factor. And secondly is the optimization based on learning. And this is in fact an implicit use of the separation principle. So we start with the filtering problem, which will reduce our optimization problem to the complete information one. So the target is to derive the conditional probability of the hidden state alpha given available information h. We refer to as the filter process and denote by pi ti that the probability alpha t equals to I given the available information up to now. And as a result, we can express the estimate version of functions of alpha as functions of pt. So here we adopt the innovation approach to do the filtering. And the essential step here is to filter all the F-adapted unobservable stochastic terms to be H-adapted ones. And that is the so-called innovation process. So in the stock price process and also the alternative data process, those unobservable stochastic terms are the Brownian motions, Wt and Bt, and also the Poisson random measure part, that is this n dt dc. And correspondingly, we can define the innovation process by these forms, that is the pi t hat and the bt hat, and also this m corresponding to the jump measure. So it can be observed from their definitions that these terms, they are adapted to age, so they are age-adapted innovation process. And if only stock price process is observed, this will readily lead to the classical one-hand filter, which the dynamic only involves the head Wt. But if we observe additionally that the alternative data here, then the dynamic will be an update filter whose dynamics will also involve head Bt and this m. So mathematically, we show that the update filter solves this following Ks system. So in this equation, we highlight that this m bar, it is a age-compensated random measure of the predefined jump measure m, and given by this form. So we call that this filter process is a jump diffusion with V-type jumps because we noticed the intensity here depend on the filter itself. And we will see in the later sections that this feature actually introduced great analytical challenges. And to illustrate this result, I present the expert opinion example in a bull-bear financial market setting. So here we assume that at random time Tn, we observe the random variable Zn, which follows two Gaussian distribution with two different means when the market is bull or it is bear. So we use the previous result, we will see that between the two signal arrivals, that is when t belongs to tn minus 1 and big Tn, then the filter process involves exactly as the one-hand filter. So it is a continuous process that only involves head W here. But at the signal arrivals, it is Bayesian updated by this function, so which is depend on the Zn and also the filter process itself. So the graph here is an illustration of the result, so it is a simulation result. So the green line here is the classical one-hand filter, and the orange knot here, it demo the occurrence of the signal and as well as the size of the signal. And the blue line here, it is the update filter. So we can see that the update filter, it jumps immediately when the signal occurs. And it also that it will be dragged towards the true regimes, that is the green line here. So in other words, we can observe that observing additional information, like here we observe additional expert opinion, it could improve our estimate of the hidden state. So it is also expected to improve asset allocation and also consumption decisions. However, we also observe that this will introduce additional randomness. So the advantage will be somewhat offset by the new randomness introduced by the alternative data. And we will also see this feature in the following section when we introduce the duality approach. So to develop the duality approach, it will be essential to define the so-called equivalent local martingale measures, Q, where under that measure, the discounted asset price is a local martingale. And when the market is complete, the set of such Q is a singleton. But because alternative data introduce additional sources of observation and therefore additional randomness that cannot be hedged by the risky asset itself, so it makes the original complete market incomplete, and resulting in a set of all such Q measures, and we denote by M as the set. And with partial information, the key is to find the projected random Nicodemus derivative of Q with respect to the original problem measure P. And we project it on the available information plane and illustrated by the graph here. So in our current setting, the set M is associated with a family of martingales given by this dt nu, and which is defined via the process nu here. So in this following form. So correspond to the M set here, we can also define the corresponding state that collects all the process nu. And we refer to this dt nu as the projected state density process. And based on this projected state density process, we can use this inequality in this theorem too to describe our admissible controls, and that is the budget constraint with partial information and alternative data. So here B and C, they are interpreted as the candidate optimal terminal wealth level and consumption rate. And the left-hand side, this equation, it is the minimum initial capital level that allows the candidate plan to be implemented. And because of the new randomness from the alternative data cannot be hedged, so we must take superminimum over the set of measures Q that belongs to this M, so which it increases the minimum wealth requirement. So combined with the filtering result, the primal problem is by maximize this objective function over the choice of set B and C that satisfy this inequality form. And now we are ready to develop the dual problem. So in this page, I list the assumptions on utility functions, which are quite common in literature. And for the presentation convenience, I define the convex dual functions of utility functions in this following manner. So now we come to the definition of the dual value functions. So we start from the primal value function that is given by this P. So it is the maximized B and C of this objective function. So now we first used the budget constraint, this inequality. So we reach the first inequality here. And then we use again the convex dual function of the utility functions. We use the definition, then we reach the third inequality here. So we will define the right-hand side as the dual problem. So it is an optimization problem over all the nu that belongs to the set theta, and we denote by d as the value function. And by formulation, the left-hand side minimum it will be always greater than the right-hand side. And we will say that there is no duality gap if we can find some y star such that the equality holds. And we see that if there exists y star and nu star such that the following condition holds, then we can check this pair close the duality gap. And if we take a closer look at this condition, it is required that the b star and c star, which is defined via the y star and nu star, it satisfies the budget constraint inequality, and in addition, the equality holds at the nu star. And a further theorem states that the existence of such a pair is guaranteed if we can show that the dual problem admits a minimizer nu star for all y. So to conclude, the problem is solved by using the following steps. So first, given the utility function ui, we aim to solve this following dual optimization problem. We want to find the minimizer uy for all y that is greater than 0. And then for a given initial wealth level x greater than 0, we aim to find the y star such that the following equation holds. And based on this y star, we calculate b star and c star, and the new duality gap theorem further verifies that actually this one will satisfy the budget constraint. And finally, we will obtain the optimal investment strategy pi star from the theorem 2. So this is the steps. And now we apply the theoretical result to a specific case, and we consider the utility function, that is the constant relative reservation type, that is takes this kind of form. And in particular, we consider that gamma that is less than 0, and also it belongs to 0 to 1. So we consider the bull bear market case and also the expert opinion example that is previously we defined. So I just here remark that in this setting, the M bar, it takes this form where the intensity measure here is given by a function of the filter process itself. And this part leads to the Duality type jump feature. And under this setting, the dual problems will take this form. And we emphasize that the dual value function is depend on the initial guess of the filter process, that is the P. And due to the Duality type jump, it will also change the probability measure here inside of the expectation. So we also remark that under the constant relative reservation utility functions, this y, it can be separated out of the objective function. So the dual problem solely consists of this part. So as suggested by the previous steps, our target is to solve the dual optimization problem. And here we first derive two important primary properties. And the first is that 0 and 1 are entrance boundaries of the filter process. So this means that they cannot be reached if the PT starts from the interior of its domain. So in other words, if you begin your initial guess, like for example 0.1, then you guess process it can never reach 0 or 1. And on the other hand, if it starts from 0 or 1, then it will immediately move to the interior and never come back. So this property actually suggests that when we characterizing the lambda, that is our dual value function, then we should not propose any conditions on the boundaries on 0 or 1, neither on the value of the function nor on its partial derivatives. And the second condition is that we show that the value function, it is bounded, and in particular, it is strictly positive. And by an application of the Feynman formula, it suggests that the lambda it should satisfy the following HAB PID equation, where the I here stands for the integral term that is colored by gray here. And because in here we are taking the supremum of the nu, then it can be observed that the supremum is attained at the nu star, which is a function of lambda. And because previously we have already derived the boundedness of the value function itself, so we will see that later it will be convenient for us to restrict the nu to be chosen inside a bounded domain. And the verification theorem suggests that the lambda is expected to be the unique classical solution to the above equation. And because of the boundary behavior, here the classical solution refers to that it is continuous on the closure of this domain, and it is C12 in its interior. So now we come to the main result of this section. So here, Theorem 3, we also actually demonstrate that it is the unique classical solution to the HAB-PIDE, and the proof of it is outlined in the following 6 steps, and those that require a special treatment are marked by a star. So in the first step, we first show that this function is Lipschitz continuous in its domain, and so we first prove the first half of this claim. And next, we show that it is a viscosity solution to the HAB-PIDE. And then we use an equivalent definition of viscosity solution. We show that it is also a bounded viscosity solution to the following PDE, where we recognize that this PDE, it is interpreted as for an unknown V, but the last term that is colored by gray, this is pre-specified, and where the lambda here is defined from our previous step 2. And this gray colored term, and we denote by I delta lambda, we regard it as an autonomous term, and that is with the lambda defined in the previous step. So here, step 3, we can show this because we use the equivalent definition, but it does not mean that a solution to this PDE is also just the equivalent to the lambda here. So we need to further show that the uniqueness of the viscosity solution to the PDE. And in addition, in step 5, we demonstrate the existence of a classical solution to the PDE. So combining step 4 and step 5, we've just verified that the lambda itself, it is a classical solution to the PDE. So combine to step 2 together, we just show that the lambda, it is C12 in its interior. So this is the outline of the proof. And now we try to go in detail. So for the first step, we want to establish the Lipschitz continuity of the value function. So the target is to establish this equation. So in other words, for 2 different given initial states, P1 and P2, we want to show that the difference of the value function is always bounded by the constant multiplying the difference of the 2 initial states. However, because we find that we are in the Levi type jump, so the measure is different if we use different initial state. So which means that we cannot deduce this result directly by using the classical approach. So this is also the main difficulties. So to further illustrate this point, I want to refer to a previous work by Free and his co-authors. So to tackle with this difficulty, they try to reformulate the state equation to be an exogenous Poisson random measure such that the law of the new process is the same as the original one. So to see how it works, we can check that the probability of original filter process that it belongs to a certain set A, given the information, it is given by this integral form. So it is an indicator function and multiplying the intensity here. So what they try to do is use a change of variable by defining a new variable u that is given by the cumulative density function f, given by this one using this definition. So by using this change of variable, they change this previous integration to the following one. So it becomes an integral over 0 and 1 du. And where the function here, it is changed to c tilde and given by this not so intuitive equation here. So motivated by the change of variable technique here, they can define a new Poisson random measure that is this n bar and define using n dsdu minus lambda dsdu. So we see that this one, it becomes is genius Poisson random measure. So the filter process here will just reduce to the very classical one, and therefore they can apply the classical result and to derive the Lipschitz continuity result. However, using this approach, it relies on quite strict assumptions on the density functions. Especially, they require that the distributions itself has a bounded domain, and the density functions here should be also bounded and continuous, and its first order derivative should also be bounded. So in our work, we try to tackle it with another approach. So we try to introduce the auxiliary process approach. So we find the reference probability measure that is the p tilde, and under this measure, we define another auxiliary filter process that is this Vt in this following manner, and the N2 is another jump measure whose intensity is given by lambda f1z dz dt. So this one is also a very classical jump diffusion with the extraneous Poisson random measure. So here we are working on the assumption that there are bounded likelihood ratio. In other words, we require that these density functions satisfy this boundedness constraint. Oh, sorry. And we also assume that it has the finite theta divergence measure for theta equals to 3. So in other words, we require that this divergence is less than infinity. So this one is a quantitative measure that used to measure the dissimilarities between two distributions. So here we can interpret this assumption as that we cannot expect the expert opinion to be too powerful. That is, it can provide us the very powerful information about the current regime state. And so given this given this auxiliary process, we can use the random encoding derivative that is linked the original probability measure to the reference probability measure. So using this kind of change of measure technique, we can smoothly derive our result. So here we finish the first part proof of the Lipschitz continuous part. And secondly, we verify that the lambda is a viscosity solution to the HGP PIDE. So by the classical definition, we say that it is a super solution or a sub-solution if for all test function Z that belongs to C12 of its domain, that the following equation satisfied. So actually viscosity solution here, the definition is trying to interpret the HGP PIDE in a weaker sense, because we do not know at once that the lambda itself, it is smooth enough. So we try to use the definition of the test functions to give a suitable definition of it. So we say that it is a viscosity solution if it is both a super solution or a sub-solution. So this is the step 2 definition, and if we want to move further, we use another equivalent definition, and that is to say that in the classical one, here that is the integrand part or the non-local part. So the classical ones say that this one is defined on the test functions, but an equivalent definition is this, that this one can be replaced to the value function itself. So we do not need to use the psi in the non-local term. We can just use the value function itself in the non-local term. So we get another equivalent definition of the viscosity solution, which leads to the PDE formulation that I introduced in the outline page. And then further, we can use this following comparison principle to show that the PDE, actually, its solution is unique. So finally, it comes to show the existence of solution to the PDE. And so from step 1, we know that the last term, that is I delta lambda, this term is Helder continuous because we proved that the lambda, it is Lipschitz continuous. But we face another difficulty, that is this part. So this part, it degenerates at 0 and 1. So because it degenerates at the boundary, so we first need to show the existence in a bounded domain that avoid the boundaries. And next, by consider a series of approximating functions and applying the interior Schroeder estimate, we can show that the existence of a smooth solution. And so by using this, we can finish the proof of the main theorem. And after characterizing the lambda, we can transfer it back to our primal problem. So we'll recall that our target is to solve the minimization problem here. So given that we have already characterized this lambda as the classical solution to the HGB PIDE, so we can find that the minimum is obtained as a y star and also nu star, where they are all functions of the lambda. And given this, and by using arguments of Deakin's result, we can derive the optimal Waltz process, the X star, given by this one, in this form. So where it also involves the solution, the lambda, and also the ZT nu star that defined with this one. And so we can also derive the pi star and C star, that is the optimal consumption investment strategy, using the following feedback form. And we recognize that for the consumption strategy here, the last term, which is partial p lambda over lambda itself, so this part will distinguish it from the full information case, and it also reflects the agent's hedging demand of the risky assets as a vehicle against the unfavorable economic regime shifts. And we will see that the effect of the alternative data is also reflected through this term, because the alternative data will come in the PDE when we characterize this lambda. So to conclude, in this study, we developed a duality approach to solve the investment consumption problem with partial information and also alternative data. And the diversified source of observation will improve estimates, but such advantage will be somewhat offset by the new randomness introduced. And based on this, we are also able to derive the explicit optimal strategies for some concrete examples. And also numerical experiments are also possible. And in the future work, it will be interesting to investigate further the so-called certainty equivalence for new information, because in reality, people usually need to subscribe or pay to receive some informations like the expert opinion suggestions or additional raw data to help making decisions. So a problem will be very interesting to investigate what price will be affordable or acceptable. And a step further, one may consider when and how to receive alternative data, and which will lead to a two-layer optimization problem. So that's all for my today's talk, and thank you.
Thank you, Kexin. Okay, so it's quite mathematical. So let me check
Yeah.
with the audience. Any questions or comments for Kexin? Let me see. I do have one quick question regarding the one of the proof should be the step 2 or the page 22. You had a quite creative move that should be one page for, yeah, this one. So the P tutor is proposed by construction, right? So
Yeah.
F1 is something, the assumption that you impose on the P tutor, and it has to satisfy the bounded likelihood ratio in the second bullet point. So my quick question here is that does it always exist? I mean, what is F2, by the way?
Oh, sorry, I did not make it clear. So actually, because we are considering the two regime case,
Yes.
so I'm considering also the expert opinion example. So the ZN follows two distribution. So one is F1 and the other is F2.
Okay.
So they are two different density process.
I see. So over there in the proof, so basically a P tutor is fixed actually, because it is by construction you construct P tutor in this way. But the second line, the bounded likelihood ratio, is an assumption, isn't it?
Yeah. It's
an assumption.
Yes, it's a standing up assumption. Actually, I need to propose this assumption to ensure that the reference property measure, the auxiliary process VT here is satisfy some good property.
Yes.
Like inside of it, the parameters is satisfy the Lipschitz condition and also the growth condition. So I can ensure that the corresponding value function can be characterized well. So that's why I need these conditions here.
I see. So another quick question is about the alternative data. So in your current study, you did you assume the ether? I think at the very beginning of this of all the slides, is the ether one-dimensional, or that could be multidimensional? The ether, I remember you used the ether in your dynamics here. I wonder whether ether has to be one-dimensional.
It do not have to be one-dimensional. I think multidimensional is also fine. But the main point is, I think, actually in the duality approach, it not matter so much whether the eta is multidimensional or just one-dimensional, because all we need is the associated the innovation process that defined through eta itself. So it is defined in this measure. So it is a direct measure that defined on delta etas, that is the change of eta. So here in my study, I actually assume that this eta is a one-dimensional one. So just like the stock price process, yes. But I think it's not difficult to extend it to be multidimensional.
Okay, I see.
Yeah.
Okay, so let me check with the audience again. Any questions or comments? Okay, if no, then let's thank our speaker again. Thank you, Kexin, and thank you all for joining this session. Thank you very much.
Yeah, thank you so much.
Yeah, I'm going to call the end of this session. Thank you all for your participation. Thank you very much. Bye-bye.
Thank you. Bye-bye.
Bye-bye. Take care.